method logs the stress over a specific device, compares it with the results of the qualification, and then by this comparison, it can say this is the health status of the system. But there are also other solutions out there, like anomaly detection. And anomaly detection does not only model like the wear out effects, it can actually detect failures throughout the whole life cycle of a product or of a system. And the idea here is by measuring system parameters, implications on specific components can be made. So for example, by measuring the voltage ripple on the output side, if this increases over the lifetime, an anomaly detection algorithm could say, for example, hey, the capacitance of this capacitor has reduced, and after a certain threshold, for example, it could say, hey, this capacitor is likely to fail soon. So here it's basically from system parameters, try to detect failures of individual components. Those methods are usually done ex situ. So, meaning that in an external entity, a computation of those parameters is done for the power supply itself. So, for example, anomaly detection, a lot of data is streamed on a cloud, and then the computation is done on the cloud. And all of those methods are based in the physics of failure. So, physical effects are being evaluated, and then a decision is made whether this component is still healthy or not. However, we don't see a wide adoption in the market because this is a really complex problem. So assuming like here in a power supply, this is an abstract view of a power supply, a transistor is failing. Here, even the failure of a transistor, if you know which component is failing, it still has a highly probabilistic nature. So the same transistor survive under the same stress for a different amount of time. And different failure mechanisms can happen within one transistor. So a lifetime model, for example, usually models one specific failure mechanism in a transistor, but a transistor can have multiple ones, right? However, in the normal case, you don't know exactly which component might fail. So you would need lifetime models for each and every component on your device. This becomes even more complex if you have multi-sourcing. If you have like a different transistor from a different vendor, you also need a lifetime model from this one. So, and as there are not publicly available or very established in the industry, those lifetime models, adoption of something like this is very difficult. But also you need to measure the specific parameter over individual components, and measuring those parameters will come with high telemetry cost. Like you have a limited number of ADCs, right? And here, usually customers do not want to spend that much telemetry efforts. But also then the digital power controllers, they have limited processing capabilities as they don't have the biggest processors usually. And then when the digital power controller wants to send this data to a cloud to do anomaly detection, usually you have like the field buses, like a PM bus, which has a very limited bandwidth. So sending all this data in the necessary resolution is very difficult. And then this becomes even more difficult if you have a lot of processing nodes, like in a multi-phase system. And then the application controller needs to manage all those different loads. And then the communication bandwidth limitation here again. And then all of this needs to be integrated into a software stack, which is already present at the customer side. And then you have like so many different people, like disciplines, who need to work together on this. You need to redo this for every design phase or for every new design that you make. And detecting the value proposition of something like this is very difficult because like how do you determine how many false positives you had and how many failures you actually prevented by your means? So this is a very complex solution or a problem statement. Our solution to this is now an in situ health assessment based on known reliability methods. What we are doing is, instead of having physics or failure-based models for each and every component, we base our solution on statistical system models based on known reliability handbooks. We only need the telemetry of the control loop. We don't need to measure temperature and voltage and everything over every component. We have a lightware firmware running in the digital power controller itself, and we are topology and component agnostic with a BOM-based implementation. But now, what is our solution? As part of the development, our customers do a reliability prediction of their power supplies and electronic circuits. Those reliability predictions are basically the methods to calculate the failure rate and the MTBF of their systems. And here there are different reliability handbooks like the Telcordia SA332, the Siemens SN 29500, or the military handbook. Those methods, we took those methods and integrated them into our digital power controller. And by measuring the real mission profiles, how you operate your device in the field, and those reliability methods of the handbook, we can recalculate the reliability of your system in the field. And in our solution, you don't need to communicate all the telemetry data to a cloud. A single scalar parameter can be used to communicate the reliability of your system to your application controller. But if you would like to log all your mission profiles and usage profiles, also those data can be logged in memory and can be read out. Now, to understand our solution in more detail, let's have a look in the reliability handbooks itself. So those reliability handbooks, they assume that a serial model, meaning that one component failure in your power supply causes the whole power supply to fail. And every component has a failure rate, a fit parameter. And this one is generic. So you have basically a failure rate of 11 failures in 1 billion hours for every MOSFET, being it Infineon or a competitor. But this is only true for a certain mission profile. So for 50% electrical stress and for 40 degrees Celsius. And now by adding up the individual failure rates of the components in of your design, you can calculate the failure rate of the overarching system. And here now it's really important to understand the acceleration factors. So the acceleration factors, each and every component has a thermal acceleration and an electrical acceleration factor. The thermal acceleration factor, you can basically see here on top, it's the Arrhenius equation. Here, how sensitive a component is to a certain temperature change is reflected by an activation energy. So a capacitor and a MOSFET has, due to the standards, a different activation energy. For the electrical stress, here each and every component has a different stressor, meaning that a capacitor, for example, is stressed by the applied voltage, while a resistor is stressed by the applied power divided by the rated power. So, and this here can be then seen in the power law you can see here. And based on those formulas, the individual lambdas of the components are increased or reduced. Here, what is also very important is that if you now boil down your design and you have specific failure rates for specific components, you can get those from the reliability reports on the website. So for example, for Infineon, if you want to learn more about what the failure rate of your selected component is, you can simply just request them on our website. Here, the mission profile is also very key, as for different applications, the mission profiles can be vastly different. So they are put in phases. That means that, for example, in a satellite, whether it's being like standby on the ground, being launched into space, or whether it's then orbiting around Earth, right? Those are very different conditions. So here it makes sense if you use those reliability handbooks to structure your mission profile assumptions into those phases. How are those reliability handbooks then usually used, like productively in the industry? They don't necessarily are used as absolute values. Here, like a common criticism is that the failure rates defined in those standards are based on very old data, and that is true. However, where you can use them very, very well is in relative comparisons. So if you have two design iterations and one of the design iteration has a like failure rate of 10 and another design iteration has a failure rate of 20, you know that the first design iteration is twice as reliable as the second design iteration. So here, by relative comparison, as long as you deploy this methodology consistently, in relative comparison, you can see the reliability of your system very well. But now, what does our solution mean for you if you deploy it in the field? Now assume that a customer has a reliability requirements based on their customers. So we have here on the y-axis, we have the failure probability, and on the x-axis, we have the time in years. Now, the customer essentially says, from 1,000 devices, I don't want more than 30 to fail in 10 years. So this basically means we have like maximum 3% of the devices are allowed to fail. Now, by calculating the failure rate, the customer can see how is my failure rate under my worst case assumptions and how is the failure rate under the average assumptions. But then once the failure rate, so then he can say, I meet my reliability requirements as I don't touch this forbidden area here essentially. But the customer doesn't see what happens to his specific power supply when it's deployed in the field. And temperature and load can be vastly different depending on where you operate it. With our solution, you can track exactly how the reliability and the failure rate of your power supply is while it's deployed in the field. Here, this purple line is basically the live feedback of our solution that the customer can read out. He can see, for example, that in the first 2 years, the failure rate was pretty much equal to the average reliability assumptions. But then, like for the next year, for some reason, the device was operated in standby for a quite long time, and it was basically very little degradation actually. But then it was deployed in the field again, and so it picked up. And then here at this point in time, for some reason, the failure rate got very steep now, and it's actually worse or steeper than your worst case assumption, indicating that this device is overstressed. Now here you can essentially use this Y parameter that you have then here at this point in time as a indicator how much it was stressed. But you can also do very powerful predictions with it. So for example, if you then take the average mission profile that you have and extrapolate it due to the logic of if you continue to use your power supply how you used it in the past, your estimated failure probability in 2 years will be that. But it can also be done differently, that you only say, hey, I want to extrapolate my mission profile or my failure rate, which I had in the last 6 months. And then you can see actually your failure rate is worse than your worst case assumption of the failure rate. And this can be used very nicely for a health status prediction. So here, if you now at a certain point in time, like for example, at the end of life, if you are worse than your worst case assumptions, then you have a red traffic light. You basically say, hey, something is wrong in this device. It's overstressed. I might need to do maintenance. If it's yellow, then it's somewhere between like your worst case and your average. You say like it's a bit higher stressed, but it's still like in allowed boundaries. And if it's according to your expectation, then you can say like it's green traffic light. Most likely, I won't have a failure on this device. And this becomes even more powerful if we have 1,000 devices in the field. If you have 1,000 devices running our solution and you see exactly in 4 devices, hey, I have a red traffic light, something is off, or you have like in 99% of the devices it's green, but like this 1% is yellow, you know those devices are overstressed. And statistically speaking, you might expect a failure here sooner than in other devices and send maintenance there. But it's also very powerful for live control. So essentially, if you have a multi-phase systems or a redundant system, and you have 2 power supplies operating in this one system, and you can track that the one power supply is much higher stressed, so the failure probability, the Y parameter, is much higher than the other one. You can adopt your load schemes, your load balancing schemes, to optimize the reliability of the overall system, so that both of them are following this dotted green line. And here, the benefit of this is that if you only manage or balance the load based on like current or temperature, it's always only balancing on the current point in time, right? But our solution, it lets you balance on the whole history of the power supply. So, summarizing, our power system reliability solution, it's a real-time system health diagnostics and power supply circuits. We continuously process the system operating conditions in the digital power controller itself. We have a reliability model which is compliant with the reliability handbooks. So accuracy is this validated. If you trust those standards, you can trust also the results of our algorithm. And with those 2 points, combining them in real time, you can calculate the failure rate of your system live in the field. So, and this gives you like an industry-proven reliability assessment by providing to you the MTBF or the failure rate parameter, which one you prefer. It helps you, especially like in redundant systems, to optimize the lifetime of your system and to improve the maintenance decisions based on this health status, which I pointed out. And with this, you can get an idea of which are the reliable devices in your population. And also the mission profiles, which we use or which we continuously measure to do these calculations, we also can log them. And here we have very, very nice features how those logged mission profiles can be saved in a very efficient way and can be communicated to the larger application controller or integration systems. And one of the key values of our solution is that it's a very easy to use approach. As I said before, the problem with those advanced health monitoring solutions, it's very often that it's very complex and very difficult to verify to have a good solution. And then if the multi-sourcing is an important topic to you, this will get even more complicated. With our solution, this will become much easier, as this works for every power topology and essentially every electronic design. And it's also already existing for our XTP controllers, digital power controllers from Infineon. And if you have any interesting projects, support of experienced reliability and modeling expert will support you in getting the solution running. So with this, I would conclude this presentation. Thank you very much for your attention. And if you have any further questions, feel free to ask. Thank you.
And thank you very much, Christian, for that presentation. That was excellent. And now we'll turn it over to Manuel, where we'll be able to address a few of the Q&As. Again, as a reminder to the audience, if you have any questions, please feel free to submit those over on the right-hand side of the screen. And so, Manuel, are we ready to answer some questions?
Yes, of course. Hello from my side as well to the audience.
Our first question says, when tracking the trend and prediction that's based on the actual usage, as we saw in those graphs, is there a way to learn from similar historic usage models, creating a trend line